Welcome to another MeteorJS tutorial on reactive data structures. This time we'll cover reactive trees, a recursive and rather complex data structure you might want to use, for example, for file system or other recursive structures that have to update reactively. And before we go into the implementation, let me show you how it looks like. So this reactive data structure website I created with Meteor, which you can see in the previous tutorials, it's easy to set up and to create, is now holding a reactive data structure called the reactive tree. I'm adding a number 1 and number 2, and as you can see, these are children of this very first root node, and then I can add children to these children, and every of them can hold other children to an arbitrary length indefinitely. And if you haven't heard about trees, the basic concept is fairly simple, but the specific trees can be very complex. So there are very different variations of trees for very specific applications. The most fundamental structure of a tree is there is a root node which can have 0 or more children, which are nodes themselves that can hold 0 or more children, and so on. That's the recursive structure. And if they don't have any children, they're called leaf nodes. And then you can implement certain iteration strategies, performance optimizations, and so on. For this tutorial, we want to focus on the most basic implementation that has some sort of reactivity. So let's first implement the ReactiveTree class, and let me explain to you how it actually works. So there is the tracker we need to implement. If you don't know what's the tracker, I suggest you to watch the previous videos there I explain tracker as the backbone of MeteorJS reactivity on the client. You can use it across multiple front ends such as Blaze, React, Vue, Svelte, and Solid, and your custom front end. And the reactive tree is just the overall structure, like the, I would say, the containing structure initiating the root node, but actually the recursion is implemented using our node class. And the node class is always a keeper of some of a value, let's call it item. So this.item is item, and then it has some children. And these children, they are represented in a plain array here. That's totally fine for now. And of course, because we need reactivity, there is the dependency, this.dap is new tracker dependency. And because we want to identify nodes uniquely across all nodes in the tree, we also want to give them an ID property. And in order to do that, you can simply import random from the Meteor random and call it random.id. It's a Meteor internal, so it's in the core. You simply need to import random from meteor/random, and it's there. Even if it's usually not suggested in the IDEs or something because it's internally used, it's a fairly good tool to generate good randomness. And the number 6 means the random ID has 6 characters of length, and that's fair enough for the sizes of our trees. Of course, you could increase this size to whatever you need, or whatever is supported. That's okay for now. That's the basic foundation of the node, and now we need some functions to manipulate the node. We need to add children. We want to remove children because this is also a feature that we might need. We want to remove a child or multiple children. And of course, we need to reactively return the children. So when some children change, the template automatically re-renders. And in order to do that, we write a function called children, which is named differently from the internal children, which start with an underscore to indicate these are internal, and the external function, the external property is called children. And there we tell tracker if it's active, if we are in an active computation, this.dap.depend which means, hey, if something has changed and you're in active computation, there is a dependency, please rerun the template. And then we can return this ._children. This is the biggest part for the reactivity, and now we also need some manipulation. So we want to add a new child, of course, and we want to remove a child. Now they are a little bit different. The child we want to add is basically given an item, and we create internally a node. So we say this.children, this._children, we use the internal children, not the function, .push. We want to push that to the internal list. And we're not passing the item, but we create a new node passing the item. This is where the recursiveness comes into play. The item gets wrapped in a new node, which can also contain children. And there we have already the recursive structure. And we also need to inform the tracker that things have changed. So we say this.dep. Not depend, but changed. This is informing all running computation to rerun. And now we need to remove a given node. And we can later on, we could also remove the node by ID. I mean, that might be even easier, because then we can use the index and then we can search. We can create a function that finds in the children the node. It's called find index. Sorry, I just had to remember what was the function. It's called find index. And then we can ask in the child if the ID is the given ID. And if the index is greater -1, we can simply call this._children.splice. That's the function removing the child at a given index. And we can also call this.dep.changed, because we have to inform the tracker that something has changed. This is the basic structure of a single node. Okay, but now we also need to implement the outer structure. That holds the entire tree structure and is allowing our templates to communicate with it. And that's the tree. And the tree has a root node. I call it _root, which is a new node holding the value null, because it's just using as a starting point. You could also implement the root node holding a value, but that would complicate things a little bit further. And I want to keep it as simple as possible for you to redo this tutorial on your own and get the most out of it, and then take the next step and implement this on your own requirements. And it also needs a dependency, a new tracker.dependency. Why we need that? Because we need to inform the whole chain of computations from the very first element. And in order to do that, we implement the root function. It's the same as with these children. The internal one is _ and the outer one is the actual one called root. And here as well, we need to tell if we are in an active computation that we depend on the current values here. Okay, we have implemented a tree that holds a node, that's the root node, that can add any items to the children, remove items by ID. But to the outside, we would now have to iterate everything. But we don't want to iterate everything. In the outside, we want to have this wrapped in a nice little function in the reactive tree. Call it the find function. It's the ID. And we're starting, it's a recursive function, by the way. We want to find a node starting from the root node, going down the tree. And the current one is always this.root if nothing has been passed to this function. So that's the starting point. You call this function find just with ID. It automatically sets current to this.root. And then we can start to check if the current node's ID equals the ID, then we can simply return the current node. That's the optimal case when we have found the node. And if we didn't do it, then we need to iterate the children. For const node of current.children underscore children, by the way, because we want to iterate the array non-reactively in that case, because we were searching for things. And there we can check if the node found equals this dot find. This is the recursive call, by the way, with the same ID but the given node. And if it's found, then we return the found element. Okay, wrapping this up, we have a function that finds any node in the tree by checking if the current node we're looking at has the same ID. If it doesn't have, we go through each of these children and see if, and this is the recursive call, if its ID has the same ID, and so on, and go through the whole list of children. And of course, if we found none of them, then it returns undefined. It returns nothing. I could also say return null. For now, undefined is okay. And now let me switch to the template side and simply implement the templates for you, just to make it more understandable. So let me first remove all that code and explain to you what happens here, okay? And then we can go into the implementation details. So this is the template file. And in this template file, the corresponding template is here. We have the tree template. This is similar to our reactive tree. Let me move it on the right side. Similar to our reactive tree and the node, we also have a split on the template. We have this tree template that will be our starting point to initiate the rendering. And then we have the node template that is basically a recursive version that calls itself. In order to do that, we simply call the root node, and for that we have a parameter n that's representing the node, will be our root node. And then we also want to pass a level, and this level is just an indicator of for the CSS to move the item on the right side. But apart from that, this is not necessary for the structure itself, just for the visualization. And in the node template, we're creating a div, and this div has two subdivs. The first one is the one that's rendering the node.item. So we're passing the node here called n, and then we're rendering the n.item. That's the name for it. But we also want to implement an input for the add and remove button. So we provide a text input and classes item input. I already wrote a little CSS to make it look a little bit cool. The width is 2 em, so it's not too big. And we need two buttons. We need a button for adding things. That's the add btn. And this button holds the ID of the node. Why is that? Because we need to find this node in order to add what we put into the input. We need to know which node we want to add. And in order to do that, we have this data target, data minus ID equals n.id. And having that, we can already add a plus here, and that's our add button. I'm copying this button simply and rename this to remove button. It also needs the data ID, and it needs a parent ID. So now how are we gonna do that? Why we need a parent ID, by the way? Because if we want to remove the node, then we're not removing the node itself, but we need to remove the node from the parent. So we need to iterate to the parent, tell the parent, remove this node by a given ID. That's the remove function we have implemented here. but we need to first find the parent. So in order to do that, we can easily pass a parent parameter independent from our implementation of the node simply by using what Blaze offers us. And you could do the same in React and Vue and so on. So that should not be a problem. And here is how we do that. We iterate the children, each child in n.children. That's the function. By the way, in Blaze, it's called children automatically if it's a function. So in Vue or React, it would be like this, for example. In Blaze, we just say each child in n.children, and there we just call another node template. In that case, n is the child. The level is incremented of the current level, which is passed starting with the 0 here. And then we just increment this level. I'm writing in a helper in the template. And now we pass parent equals n. So the node that has been passed to this upper template is actually the parent of each of these children we're calling here. That's how we achieve this level of nesting. And with that, we should be good to go. There's one thing left I want to implement here, and that is give me a style margin left. This is where this level comes into play. We basically use level rem, and then it's not left, it's margin left. That's the level rem. So it's no margin for the 0 level, but because we're incrementing the level on each recursion, it will become 1 rem, 2 rem, and so on. And that was how the items were moved from left to right. And now we need to implement the JS side of things. And this is not much to do now. We have a shared object here for the tree. Why is that? Why we don't add the tree on this very template here? Because we need to exchange this tree, this reactive variable tree, between the templates. I show you in a second how it's done. When the tree template is created, we initiate the new tree. Shared.tree is a new reactive tree, and then we automatically have the root node. And we need a helper for that to get the root. So in that helper, we simply return shared.tree.root. This is our initial reactive call. And now we are already on the node level, because this is only for initiating things. The rest is happening on the node level. We create our incrementing function, increment number. So we return number plus 1. That's helping us to increment the level to move the items from the left to the right. And now the missing implementation for adding a node and removing a node. And this is quite easy now. So let me reload the page and see where we are already. Yeah, we are here. There are also no errors so far. So let's first implement the add function. You can't do anything right now because the add function is not implemented, but we can do that. It's easy. We get the item using our built-ins instance.$item minus input. And if you take a look here, this is the actual input, item minus input. That's the class name. We use it to reference this input, and then that's the element, and then our value is basically $item.val. That's like a jQuery function giving us the actual value in that input. Then we try to get the ID using the data minus ID we pass on the template. Look at here. There is this data minus ID is the node ID, and we can get that from the event because we clicked that button. So we can just say current target. We could use data set.id. I usually prefer .get attribute and then data minus ID. But the other one should be valid as well. And now we need to find the parent to add the we need to find not the parent, sorry, we need to find the node to this that corresponds to this ID. And for that we use shared.tree.find by ID. That's the find method we have implemented here. That helps us to find the corresponding node by the given ID. And now we just say node.add value, creating a new child node on the given node we want to add. And we also want to clear the input, item.val null, clearing the input. Let's try that again and see how it works. Doesn't work. Maybe there's an error. Maybe it just, oh, it works. Okay. You can see now adding nodes. Could even use empty values. This is on you to validate these things. You can do that, as you can see, indefinitely. But now we need to remove them. And as you can see, we can't remove them. Oh my God. So let's implement the remove function. That's the last thing we need to implement to have this fully working. We get the ID again. ID e.current target get attribute data minus ID. It's the same as we used for the add function, but now we also want to have the parent ID, and that's data minus parent. That's the one we attach to the remove button. Then again, we need to find the node that is part of that is basically the parent. So what we need is find the parent node, find the node by parent ID, and now we can call parent.remove by ID. Okay, what? Oh, sorry, that's the node remove, and then the given ID. Let's see if I add the typo. That's good. ID, parent ID, node. Find the node from our shared tree, remove the node, and then that's calling this function. Let's try that out in real time, in reality. So we add a node, we add another node, we add another node, and we remove that node. Nice. And now we can even say we add another node and another node. And if we remove that node, it will automatically remove itself with all its children. So this is your implementation. There's a last thing you need to do, very important, when you're using Blaze at least. You need to write another function template on destroyed function, and you need to set shared.tree is null, because otherwise it would keep a memory, because this is outside of the template lifecycle. This is very important that you do that in order to prevent any memory leaks, especially if you're using large trees. So again, let's look again on our implementation. You have a root node, you can add, sorry, I forgot to call it template.node.onDestroyed, and then it's all working. So let's do a recap on that. We have our template. We can add basically on any level. We can add as much as we want. We can remove them. There was an error here. That's shared tree is null because, of course, because we don't need to use node, but we need to use template.tree_on_destroyed, because otherwise it would get destroyed already when one node has been removed. So let me move that up here. And then we're finally there where we want to be. And I hope this helped you to have a starting point for a recursive data structure representing recursive tree-like data. And if you want to know more about reactive data structures and you haven't watched the previous tutorials, take a look at our previous tutorials, Reactive Stack and Reactive Queue, and leave a comment if you want to know what we should cover next. And if you think this was helpful, of course, raise a like, please. That will also help the algorithm to better find this video. And if you don't want to miss upcoming tutorials and streams, then subscribe to our channel. My name is Jan Küster. This is MeteorJS community, and I wish you a happy coding.